Okay, I think it is just time to start our next talk, and I repeat that it is pleasure for me to introduce Professor Sergei Fedotov from University of Manchester, and the topic is space-dependent variable order fractional master and diffusion equations, anomalous aggregation of particles. Please.
Okay, thank you for invitation. A special thanks to Enrico. And of course, it's an honor to dedicate my talk to Mark Mearshart. I met him many times in the United States, and we talk a lot. And especially, well, I learned from him a lot, especially his view of probabilistic view of anomalous transport. Okay, today I'm going to talk about space-dependent variable order fractional master and diffusion equations. First, let me give a brief outline what I'm going to talk. First, of course, introduction, anomalous transport, intracellular transport, fractional PDE. Basically, I'm going to give you motivation why we're so interested in space-dependent fractional differential equations. Actually, I'm going to give you three motivations. Next, I'm going to give you our results on the solution, asymptotic solutions of fractional diffusion equations. And finally, I'm going to talk about intracellular transport, because the transport inside cell usually anomalous, and well, it's almost like paradise for us, for those who are interested in fractional differential equations. Okay, so first let me start with time fractional Fokker-Planck equation. Well, it's a very nice equation. It involves three terms. On the left-hand side, we have Caputo derivative, advection, and diffusion. And it involves three terms. Now, can I have your attention? Look at this. This is drift, depends on x. Diffusivity depends on x. What about this? Alpha. Why it's a constant? Do you know the answer? Why we keep it constant? Of course, if you want to make it dependent on x, can we do that? Here, put alpha depends on x. What do you think? As far as is continuous time random walk is concerned, we can't. Because we always need to think what is underlying random process, not simply put on the left-hand side Caputo derivative. So this is the first motivation. And now let me show you just diffusion equation. This diffusion equation first derived by Churchkin, Gorenfo, and Sokolov long time ago, 2005. And now look at the structure of differential equation. You see, on the left-hand side, we have Riemann-Liouville derivative. Anomalous exponent now, I use different notation, mu. Of course, it varies from 0 to 1. Under this operator, can we switch Riemann-Liouville derivative to Caputo derivative, as usual we do? The answer is no. So it's quite difficult equation, and I'm going to give you the idea how to derive this equation in a minute. But now look at this equation again. The reason why we put constant here, because it's relatively easy to find stationary solution. So, for example, if this is constant, we have a very nice Boltzmann distribution in long time limit. And the only impact of this Caputo derivative is just slow relaxation to stationary distribution, not exponential, just power law. That's why we like Mittag-Lefler function a lot. And of course, if diffusivity depends on x, yesterday we heard about a lot. It's a Leonenko talk, a very nice review that depending on the how its diffusivity depends on x, we might have different stationary distribution, depending on, of course, boundary condition and finite domain or infinite domain. What about this? Do we have the same property? do we have stationary distribution to that equation, similar to this one? And the answer is no. And that's what I'm going to show you. So this is basically first motivation. But in fact, it's very difficult to deal with this equation because we see this operator inside Laplacian second derivative. If you don't believe me, ask Bruno. He also shared that opinion. It's not a trivial equation. I will show you how physicists deal with this equation later on. So second motivation. Okay, second motivation. I asked my PhD students several years ago to solve this equation. I told him, look, this is very difficult equation. Let us solve it numerically by using Monte Carlo simulation. So we consider finite domain X varying from 0 to L. Of course, here we have P. It might be density of the particle. It might be probability density function. Now it doesn't matter. Okay, so we put zero flux at 0 and L. And I ask him what happened with this initial distribution, provided the dependence of anomalous exponent mu is the following. Of course, it varies from 0 to 1. It's constant, and then we have a small peak like this. So a small variation of anomalous exponent, small deviation. If I ask you, for example, if we change slightly drift or diffusivity, do we have a drastic change in a stationary distribution? The answer is no, of course. Of course, it will be modification, but not drastic. Okay, what happened with this example? I remember Steve Falcone came to my office. This is a story. And he told me that, boss, I have a trouble. It doesn't work. Algorithm doesn't work. I always have rubbish all the time. Actually, he used the algorithm developed by Enrico Scalas. I told him, no. I told him, I trust those people. So something wrong with your procedure, with your coding. And okay, show me the result. And he said to me, well, when I use this small tip or small hole, instead of relaxation of this non-uniform distribution to uniform, then I've got the following. Everywhere 0, apart from this area. So Monte Carlo, it's something like that. And 0 everywhere. Of course, for student, it was rubbish. And in fact, we call nowadays, it's anomalous aggregation. So there is no relaxation to stationary distribution. And all particles at the end trapped in this area.
The algorithm would work.
Well, of course. By the way, that's algorithm to generate random numbers corresponding to Mittag-Lefferer function. Okay, so actually we discussed that phenomenon a few days with Bruno, and I like the way he put this. Do we call this diffusion equation? Because when we have diffusion equation, we assume spreading, correct? Of course, for standard diffusion, we have a very beautiful normal spreading. For subdiffusion, we have, of course, slowed down, but still spreading. What about here? Do we have spreading here? We start from here, and then anomalous aggregation, quite opposite. So it's not diffusion equation. And at that time, I thought this is really bad equation, because in mathematical literature, if you have change parameter of the system and you've got drastic change, it's a bad equation. But later on, I thought, well, no, it's a good equation because I've got anomalous aggregation. You know, in mathematical biology literature, they call aggregation as the interaction between advection and diffusion. Usually, we use chemotaxis idea. We have a diffusion, but if we have a force driving particle one side, at the end we have non-uniform distribution, and that they call aggregation. But here, clearly we have anomalous aggregation. Okay, I'm going to discuss this, of course, later on. Now,
sorry to interrupt you.
Yes.
From let's say home, they have some trouble in following the presentation because they cannot see the blackboard. Like probably, let's say it's hard to have both slides and blackboard. Maybe if you can reduce the amount of use of blackboard and just stay on the slides, I think it may be easier for them to follow.
So you suggest just to show slides?
If you can, probably. Okay, so
okay, I will show you just slides, no problem. And the third motivation is biological. Recently, we performed several experiments. Not me, my PhD student, Daniel Han. Okay. Oh, yes.
And also, just to make you realize, maybe when you point on something on the slide from home, they cannot really see. Maybe if you use this thing, but
this one.
Yes, I'm not sure they can realize what you are pointing with this thing. So,
but at least you realize that.
Yes, that's for sure. From here, we don't have problems. I'm okay. Thank you.
Okay,
sorry.
This is two cells, very dangerous cell. It's a cancer cells. You see two nucleus, and look at these green spots. This is lysosomes. Lysosomes, very important creatures inside our cell, and they degrade macromolecules. Viruses don't like lysosomes because lysosome most of the time kills viruses. And now you can see that lysosomes non-uniformly distributed inside cells. So these are cluster and then concentrated near nucleus. And of course, some of them on periphery, somewhere here, here, even here, but most of them concentrated here. Also from literature, biologists saying that they move, but their movement is subdiffusive. And of course, I asked my next PhD student, Daniel Han, oh, let us apply this theory to that particular case. But of course, we need some evidence. And then I asked Daniel to measure from experiment, not just theoretically, measure anomalous exponent here near nucleus and on periphery. He analyzed trajectory, and he found that anomalous exponent near nucleus is smaller than outside on periphery. Of course, this is due to overcrowding near nucleus. A lot of creatures, Golgi, mitochondria, name it. So I said to him, okay, now it's time to analyze that equation. Not just numerically, but we'll try to do it analytically. Okay, so this again, the idea, what we have behind that equation. And let me remind you, that equation derived here. Oh, 5 years later, Nikolai Korobel, my postdoc now, and Eli Barkai, they wrote a nice paper, but they did not solve that equation. They're physicists, they're just smart people. They just think, okay, why we should care about distribution? Just split the whole space into two subspaces. In one case, you have one anomalous exponent, it's another one. And of course, they got very interesting result. But they did not look at the solution to this equation for particular distribution of anomalous exponent. And recently, mathematicians started to work on that subject. And Saurov is going to give a talk, I guess, on Friday about this topic. And Bruno. And now let me show how we solve that equation. But before I solve that equation, I thought, is it good equation? Is it unique equation? because that equation not given by God, it's given by Churchkin and influenced Sokolov. So, and then you see, that's very important. If you open any book on transport, you can see that standard equation, diffusion equation with diffusion dependent coefficients look like this. So the rate at which density varies, this is last time, sorry, minus derivative of the flux with respect to x. And the flux is minus diffusion coefficients. Now it depends on x. And the gradient, of course, sorry, with respect to x. If you substitute this here, you've got different kind of equation. First derivative with respect to x, d rho dx. You see the structure. Look at here. We have here Laplacian, second derivative, and then product. But in standard book on transport, we had that equation. You see, diffusion now depends on x. And we started to think, probably it's not unique. And we derived another one. This is just another version. So now you can see this equation close to this one in terms of structure. Okay, but now instead of second derivative here, of course, we have first derivative and the product. And again, this is standard Riemann Liouville derivative. What is the best model? This one or this one? We still don't know. So you can derive variety of models. Okay, let me show you how to do it. So this is a standard model. If you consider a lattice, 3 points, and then writing the balance of the particles, so the rate at which the number of particles change at a particular point, of course, some particle coming from the neighborhood and escape. And as long as you assume that trapping time is distributed according to Mittag-Leffler function, it's very easy to show that escape rate can be written in terms of Riemann-Liouville derivative. If you substitute this here, here, and here, it's obvious this is just Laplacian. And you just take the limit, a tends to 0, and you come up with standard equation. But for barrier model, that's what we invented, you can think in another way. These are two escape. Some particles escape on the right, some on the left. But then they have to overcome the barrier. That's why you see escape on the right depends on anomalous exponent, not at the point x, but at the point a plus 2. At first glance, you can say, well, when a tends to 0, this is standard diffusion approximation, you will end up with the same equation. The answer is no. You will end up with this modeling with this equation. And let me tell you, this equation got all nice properties. You start from non-uniform distribution, and then you will get uniform distribution at the end. So there is no unique way to define fractional equations with space order variable parameter. There is no way. So you can define many of them, if you, of course, consider continuous time run-the-ball model. Okay, that's a message. So basically, I had several messages. If it's inside operator, Riemann-Liouville derivative cannot be switched to Caputo derivative. That's the main thing. But this operator induced many interesting phenomena. So exactly, absolutely. That's very good comment, because in the mathematical literature, in biology, they also take into account dependence of the rate on X, and that's the way how they induce chemotaxis. Correct. Okay, now it's very interesting result. If you write down our equation in a standard form, and then try to find the flux, you will get the following. Okay, can I have your attention, because that's really important result for our research. Look at the first term. Of course, this is standard diffusion term. But then we have advection. And advection proportional to the derivative of anomalous exponent with respect to X. If you consider anomalous exponent increasing function with respect to X, this derivative is positive because of negative. This is advection term, which drive particle at the place where anomalous exponent has the minimum. But now look at this operator. This is just mathematical technique, nothing else. To recognize this operator, it looks like a Riemann-Liouville derivative. But look at this guy, this extra logarithm factor. Do you know this operator? And you see, in my opinion, this guy is responsible for anomalous aggregation. He drives particle from the right to the left, and he's very strong. Why he's strong? Because next step was, okay, let us take into account the force in the usual way, in the Fokker-Planck equation, acting in this direction. No way. This is a dominant term. He drives particle at the minimum of this function. And let me show the solution now. If you are interested in how we managed to get solution, please read this paper. And this is distribution. So you see, we start from uniform distribution. And this funny fractional advection term push particle from the left, oh, I'm sorry, from the right to the left, in a such way that this point increase as a logarithm t. So extremely slow. So advection, and that's why we call it anomalous advection. Because when you consider any Fokker-Planck equation, fractional or non-fractional, you always have a balance between diffusion and the force. And as a result of this balance, you've got stationary distribution. We know that. But here, no stationary distribution, because this guy goes up, up, and up. So in the limit, it will be delta function at the point 0. But because of this extra slow growth, you should wait a long time. There's no way, even numerically. Okay, that's a nice solution. Oh, by the way, if I ask you, for example, just check your intuition. Anomalous exponent, mu, behaves like this. Let's say 0.5. Constant jump. Constant jump. Hole. Something like that. What would be the final state? What do you think now? Yeah, it's easy to check numerically that all particle will be here. The reason why I'm telling this, because some people are saying, well, in heterogeneous medium, anomalous exponent is not constant. And what they're doing, they introduce distribution of anomalous constant and integrate Caputo derivative. You know that, of course. But if you integrate Caputo derivative, you've got everything the same. Slowly, but still you've got stationary distribution. For that particular case, for freezing heterogeneous medium, you don't have that effect. So all particle will be here at the end. Right. So I still have time. Oh, okay, 5 minutes. Oh, that's what I already mentioned. So if you use Fokker-Planck equation with a drift, and this is again standard derivation, there's no problem, then you expect that, let's say, with this drift, you will get Boltzmann distribution, something like that. And that's what we have as long as anomalous exponent is constant. But when mu depends on x linearly growing function, then again, this anomalous advection drive all points on the left-hand side. No choice. And again, it's distribution because, well, also we formulate, this is, will be very short, we formulate master equation in a similar way. We solve this master equation asymptotically, and then the solution also converges to the solution we obtained for fractional diffusion equation. So there is a nice correspondence between master equation and diffusion equation. Right. And finally, this is experiment. Of course, because we motivated by lysosome distribution, Daniel measured the distribution of lysosome inside cell, and we have this distribution, which really good fitting for our distribution. And it's, again, it's not stationary. It's always changing. And this is anomalous exponent for real cell. Of course, it's a huge variation. See, this one, this, but this is a tendency. It's increasing function of space coordinate. So if we move from nucleus to periphery, anomalous exponent increasing. That's what we measured. Okay, and finally, well, now we turn to transport of vesicles, organelles inside cells. And in fact, this is a cell, and this is just tracking of particle. And the particles now moves not subdiffusively, but superdiffusively. Because if the particles start to move along microtubule, you know, it's getting better and better for some reasons. And the run is pretty long. And of course, I ask again my PhD students, please measure running time. So we assume 1 over t, 1 plus alpha. And he fit this power law of running time distribution. Clearly, we have 1 plus alpha. That depends on alpha, whether we have first moment or not. And exactly from experiment, alpha was 1.6, which means first moment is finite for running time. Second moment is divergent. Believe me, I was so happy when you've got from experiment this kind of distribution. And that was Levy walk. I remember I almost hugged my PhD student. Because you're just waiting and then bam. And of course, probably for a neuron, when it's long, alpha less than 1. And then, of course, we will have ballistic motion. And that's what we discussed with Bruno, because some people like ballistic movement and might be happening in biology. Okay, so, oh, that's a experimental determinal survival function. So it's not just modeling, it's directly we managed to get survival function of the particle on microtubule and show that all this funny power law distribution. Of course, for real life, there is no power law because the size of the cell is small. So sooner or later you have to cut. And again, it's good for us because it's a temperate fractional analysis. So as I said, intracellular transport, just paradise for us. And if you are interested, I'm happy to talk about all this transport inside cell. Because I'm going to finish. 1 minute left. And this is my collaborator. Because of course, this kind of research you can't do like on a desk doing your little formulas. You have to collaborate strongly with experimentalists. And this is Vicky Allen. She's professor of cell biology. She doesn't know mathematics, but the way she thinks so clear that you just talk to her and just want to write down equations immediately. It's really beautiful. And Thomas Way is biophysicist. He was always like a translator between me and Vicky Allen. Oh, Nikolai, my postdoc. Daniel Khan, he left me recently for Cambridge, which is shame, of course, but what can I do? So that's our multidisciplinary group. Thank you very much.
Thank you very much, Professor Fedotov. Brilliant talk, very interesting and with a lot of nice applications. Do you have any questions or comments?
I have two questions. First of all, how exactly does the you said it approaches a delta function, and then you show this increase with x, and
yes.
So do you know it diverges like a power law, I guess, the x dependence for finite time.
Okay, let me show you.
So the question is, this will depend on the slope of mu. Close to the minimum.
Oh yes, of course. That's a very good question. The slope of mu should be finite. So if it's not finite, like a minimum, then of course first derivative is 0.
So
and this is very separate case. We did not deal with that. If I would guess it's even slower.
Yeah. So do you know how does it exactly diverge? I guess it's in this gamma function you can calculate.
Where?
So how does it diverge close to 0? I mean.
Oh no, it just looks the factor.
The
so you see, this is a ratio.
Not with
it's a power law.
Not with time.
And
with
this
x.
is log.
With x. With the position.
At 0 position, yes. So if you put
No,
x equal to 0, this delta mu equal to 0. And you've got just logarithmic growth.
No, I'm looking at least as a function of x.
Oh, if it's here, then you have a product of this function and this power law function. And delta mu is the difference between this dependence and the value of mu.
Thank you very much. So delta mu is not equal to 1.
No.
Okay.
This is just difference.
Yes. Any more? No. Yes.
Thank you. I have a rather silly question to ask. If the distribution is not stationary, shouldn't be the fractional order also be a function of time, not only in space?
No. The reason why we have space dependent, because we have trap, which and the strength of the trap is different for different position, but the medium itself is stationary. Okay. That's why there is no dependence on time. But of course, it's easily can imagine that if the environment change with time, it's even more complicated.
And then you will end up having
you end up with
function
trouble,
of time as
definitely.
well. Yeah. Okay.
Can you hear me?
Yes.
Thank you, Sergei, for the nice talk. Probably something I forgot to ask you when we were discussing is the following detail. From the analytical point of view and probabilistical point of view, it makes a crucial difference when if the function mu of x is continuous or not. from the modeling aspect, so in your model, there is a crucial difference.
Yeah, that's
under
clear.
this.
And I could explain. If you've got the jump in mu, that difference, the gradient is finite, so it's a jump, and the force actually of driving depends on this difference. Remember your paper, if you have a difference between mu, finite difference, you just drive particle from one space to another one. But if it's continuous and you consider the limit when the distance is getting smaller and smaller, at the end you will get that difference very, very small. So that's a huge difference. And that's why we consider master equation with finite difference. But then we look at the limit when the difference between neighborhood is just getting to zero, and still we have that phenomenon. But yes, I absolutely agree. It slowed down.
More questions?
Maybe a very quick one is more like for my intuition. So these extra inhomogeneities in the mu of x.
Yes.
So probably is something that will depend also from cell to cell. Is not something that is equal for all the cells, let's say. Or I was just wondering, like, there will be a microscopic picture and a macroscopic one. So supposing that we want to go from the motion of each single particle to the motion of the density of particle.
Yeah,
Is it still correct to like expect like this mu of x dependence, or there will be like a, let's say, average value of mu that will appear in a macroscopic point of view of this dynamics?
Yeah. It's a very good question, because nowadays very popular in probability. We call it mixing model. In physics, they just too hype, call it super statistics. And of course, if you look at that equation, yes, if you assume that mu is some kind of distribution and change because of heterogeneity from cell to cell, you can put extra probability function and integrate, but then you might end up with a quite complicated mathematical problems. But yes, it's the right direction, because cells are not the same. Absolutely, I agree.
Okay, thank you very much. Do we have much more questions or comments?
I have one more question.
Okay, please.
Hi, Sergei. Nice talk. Enjoyed it very much.
Hi,
It's Boris here. I'm just wondering about your intuition. I understand that if you have your fractional derivative depend on x, that in the end the particles end up where they age the most and where they are stuck the longest.
Yes.
If you had tempered fractional derivatives, so if you don't have infinite moment to stay in there, but a finite moment, do you still think you would end up in the deepest trap, or would you have a distribution around it?
Yes, of course, Boris. If you allow particle to escape somehow mathematically or physically, just go, then of course this effect will disappear definitely, because this very much depends on that infinite first moment. That's my answer.
Thank you very much.
Thanks.
Do we have more questions? Okay, if not, let's thank the speaker again for beautiful talk.
Thank you very much.
Now we have time